and sharing our YouTube channel. So you can see this later. So today we will have the Australia perspective in context of how we can integrate the research and the science into the operation. And I'm very happy that today we have today so important people here. Not so only important, but we have a lot of knowledge, different knowledge here today. So we will learn a lot. So only to give you the short presentation about the NERO project. So I will share with you 4 or 5 slides, and after that I will pass or our moderator. It will be Melissa from New South Wales. And today we will have Mika Peace, John Runcie, Jason Sharps, and Simon Amstrad. So, but after that, Melissa can explain better than me who will present today. So, the NERO is the European networking in context of the extreme fire behavior. It's cost action is a cost action funded by European Commission. Here you have the website that you can see more information about this cost action. The NERO is mainly the networking platform. So here you can see mainly the 4 different ways that we can interact and how this project could be uh, how you can participate in this project. So we are doing in the last year we did, I think 9. I don't have sure the number, but we did some short term scientific missions. He's This kind of missions could be important in order we exchange experience with the researchers and the practitioners. Usually we have some subject to develop and move people into different across different countries, and in this way we can develop more about this specific subject and work together in these 2 different roles. These roles that I'm speaking about is research and the practitioners. So we are seeing that this kind of methodology is very important in order we try to work together in the field during real situations. Also about the some conference, we will have other one this year in September, and we can give some funds and when in order to participate in conference. So is the narrow this cost action is about networking and can found mainly to exchange experience, exchange knowledge, and cover all the costs when we talk about conference, short missions, and also virtual mobility. So we are doing or we are trying to do this kind of the webinars monthly, and this webinars is into the work group 3. The NERO project is divided in 4 work groups. The work group 1 is about the historical extreme wildfire events. We are trying to collect information and trying to develop the database about extreme wildfire events, and it's crucial we develop this kind of information in order we know more about our wildfires. And when I say more about our wildfires, I'm saying about some descriptors during the event. The work group 2, this leading by George, is here now, is trying to process all this information and try to create with this information, try to create knowledge, try to create some products that we can use later. So after we collect all this information, we have a work group that is developing all this information and trying to convert and knowledge all these things we trying to use with the capacity building. I'm leading the work group 3 with Nuria Prat from Pau Costa Foundation. And the work group 3, we are trying to develop training, these webinars, and try to disseminate all this information and try to apply and convert information and real apply or real application in the field. And the last one is the work group 4 is about communication and dissemination is very important for us. So it's the way that we can communicate with all the people. So only for give you the perspective of this webinar, work group 3 is managing these webinars. As I said, we are trying to do this in monthly, but in some months it's very difficult. And today we are starting the series of the 4 webinars with the 4 different countries that we think that we have good examples, and maybe we have the different perspectives how we can integrate science and into the practitioners or into our organizations, how the science can contribute mainly in the before the event and during the event when we are responsive. So if you need more information, I have here, we can see here my email and also the Nuria Prat. And today I will pass to Melissa that will manage all this webinar. So let me I would say that today, this webinar, we have the collaboration of the Pau Costa Foundation. So also Lucy is here managing all this technical stuffs. And thank you very much for this important collaboration. So Mel, floor is yours. Thank you very much for your participation. I will stop to share my screen and go ahead. Thank you very much.
I'll take it from here. Well, hello, everyone. I will say good evening because at the moment in Australia, it's towards the end of our working day. You might also notice that all of our presenters are wearing jumpers because we've recently had a cold snap. So very interesting evening to be talking about wildfire in Australia. I will just quickly share my screen and we can get started. So my name's Melissa O'Halloran. I'm the Manager of Bushfire Risk Planning at New South Wales Rural Fire Service. So I look after our planning and preparedness space. I have been a fire behaviour analyst, but not necessarily the role that I always go to. But we've got a really great lineup today. The first thing that I would like to do is an acknowledgement of country. So a very important part of Australian meeting culture is that we acknowledge the traditional owners of the lands and the waters across our country. We're really privileged to be able to work on this land, and we thank the traditional owners for their expert care. Where I'm calling from today is Wongal country. I would like to pay our respects to the elders past and present and recognise their connection to the country and their ancestors. So a little bit about Australian and sort of the Australian fire management context. We're dealing with a very large landmass. And just a little bit of a comparison here. All the countries of Europe are only 1.3 times larger than Australia. And while we do quite some things at a national level, a large part of fire management in Australia is at a state level. So I work for the state-based agency in New South Wales, and as a comparison there, we have New South Wales is quite significantly larger than France, where I just randomly picked one of the larger countries that I was aware of in Europe. So we do a lot of our governance and management at a state-based level, but we do all of our operations and planning at a local level. So we do at the national, the state, and at a local level. Our research community is largely working across all of those. So that is, I guess, one of their massive challenges, is that they not only have to deal with us, but they have to deal with our sort of counterparts across other parts of Australia. At a national level, we do have our AFAC, which is the Australian Fire and Emergency Services Council. It's a independent member-based organisation which we all sort of participate in, but it doesn't actually have a specific role in terms of fire management. So they help out with coordinating training capability, and so in particular the national accreditation for the fire behaviour analyst role. That's where we do our national resource sharing. So when we send crews to other parts of the world, at the moment, yesterday we just sent quite a number of people to Canada. They went as Australians, but they were all from different fire agencies across the country. At a federal level, we also have coordinate some of our aircraft, although in New South Wales we are now building our own aviation capability as well. So a little bit about the size of what we do. Just flicking through. I've got a slide here, which is a very old slide. It's part of our, from the Bureau of Meteorology, part of our sort of fire weather information, and it talks about, I guess, the fire landscape in Australia. I guess the point that I want to point out here is that all of Australia is considered fire prone. And there's quite some variation across that. So traditionally, we've had a fire season that starts up the north of the country and then moves its way progressively down through the landscape. What we're finding is that that's not how things are happening anymore. We are finding, all areas there's changing fire landscapes. So in the north of the country, we've traditionally had a lot of grass fires. And with these, they burn very regularly, large areas, very large fires, and large areas, to the point where early season burning can actually compensate for the carbon emissions in the late season burning. So that's something that's been able to be part of the mitigation programs up there and provide the local landowners with some carbon mitigation benefit. But we are seeing a lot of our sort of wetter rainforest areas, which would traditionally be in the north of Queensland, isolated areas that might not have burnt. Well, we are seeing those burning now. So while we've traditionally had this sort of landscape of all of Australia being prone to fires, there is quite significant changes, and some of our presenters are very clear experts in this field. So we do have this changing climate. We are seeing a lot of different things. So, for instance, over the recent decades, we have seen fire seasons changing on the south coast of New South Wales. They're on average starting 3 months earlier. So where we had traditional patterns of how we would share resources, where we could move them to one part of the state and then they would progressively move as the season progressed, these assumptions are no longer held. So we are having to find new ways to do things and new ways of explaining the observations we're seeing as firefighters. And this is some of how we've sort of built some really good relationships with our interstate counterparts, and then also the research community as well. I'll just quickly mention a little bit about our New South Wales. So within New South Wales, we are one of the fire agencies. There are 4 in New South Wales. There are 2 fire agencies. So we're the Rural Fire Agency. And I probably should mention at this point, you will probably hear the word bushfire used throughout our presentations rather than wildfire. The title of this seminar was about wildfire. We traditionally use bushfire in our language. And an odd quirk in New South Wales, bushfire is 2 words, not 1 word. The rest of the country sees it as 1. So these are just a couple of the language things. So all of our policy and doctrine and procedures use some slightly different language to what you'll probably find Jason and Mika are very familiar with wildfire, because they're generally publishing to an international audience. So in New South Wales, we've got 4 fire agencies within the Royal Fire Service, and like a lot of our fire agencies across the country, the vast majority of our workforce are volunteers. So in New South Wales, we've got 71,000 volunteers that have the same training and do the majority of the work, whether that be in bushfire mitigation or whether that's in response. They also perform a whole lot of other functions within their local communities, because these are the representatives of the community that come along, and they'll fight fires, and they will also respond to storms, even things like car accidents and those sort of things that are important within their local community. So that's a little bit about our agency. But I want to talk a little bit about, I guess, some of our examples, and we will see some of these from our presentations today. In 2019, 2020 was our very large fire season across Australia, particularly in New South Wales. There's a picture here of our State Operations Centre. So this is where we sort of coordinate firefighting at a state level. So all the agencies come and we work together. So we have our embedded meteorologist, and for those who know, that isn't actually a meteorologist sitting at a desk, it's just an actor. And then we have our resourcing crews in the sort of the middle circle, and the outer circle is all of our liaison officers with all the different agencies across government. You can see to one side of the screen, off to the side, is where we have our media team, and the other side, hopefully for this audience, where all the magic happens, is where our fire behaviour analysts sit. And so we have a really large fire behaviour analyst capability, and Simon will probably talk about that, given that he had a very key role in setting that up within New South Wales in particular, but an influence nationally. And that's a really big part of how we gain our intelligence within our fire operations. One example, so Mika, who will be our first presenter today, I'll introduce her a little later, but she was our embedded meteorologist for a very large part of 2019 and our very big fire season. And I do remember on one particular morning, I was just walking past, but was always very interested to hear her briefings. And she was mentioning, and I'll probably get some of this wrong, so hopefully she can correct me if I'm wrong, was talking about just the area that had been burnt and how it had changed the land cover. And so that was affecting the forecast. So where the forecast had taken into account that we normally had like forest cover, and now it was black and was changing the reflection and the behaviour of the forecast. So that opportunity to have that meteorologist with this really broad sort of strategic knowledge was able to feed back in directly while we were operational. I probably spent more days with Mika over that summer than I did with my own family. And so there's some of the ways that we sort of start to include the research into our operations. As a result of that fire season, we had a very large inquiry. Now, these are some of the statistics for New South Wales, but this was also fires that affected quite a number of states of Australia. We lost 26 lives in New South Wales and nearly 2,500 homes. And one of the things I wanted to point out about this inquiry is that we were really fortunate that we had some great people running it, but they were also very, very willing to listen to their expert witnesses. And so I'll particularly mention Jason Sharples, because there's a number of the recommendations that were as a result of him being able to provide input to that inquiry, to be able to explain the science of some of the things that we saw in that fire season that we hadn't seen before, and was able to then we were able to develop some really practical and pragmatic recommendations which we've now spent the last couple of years developing. And so there's been a lot of change for our organisation and how we manage fires in Australia since this large fire season. We have fires every year. We have thousands of fires every year. We have had, particularly in 2023 and 2024, we had fires burn in areas that had burnt in 2019, but we haven't had a season of the scale that we had in that 2019 fire season. And I guess the negative outcomes, but also then the positive opportunities to be able to learn and develop new ways of working from that. So I just, in sort of wrapping up, and I'll spend, hopefully we'll get most of the time with our presenters. We are looking at a whole range of ways of how we can incorporate the science and knowledge and research. And John will talk about an exceptional example of this, where we've had a national project that has really, to be honest, I'm not sure that John will tell the story, but it had a couple of goes at getting up and running to change the way we do our sort of fire danger ratings. And the model that worked was having a science team connected in with the science community, embedded within a fire agency, so then they could work on a daily basis with all of the agencies around the country. And it's been a massive effort to significantly overhaul not just the science component, but the communication and the policy and the implementation has been just such a massive success in Australia, and definitely something for others to learn from. So that's all I have to talk about. What we'll do is we'll go through each of the presentations, and so I'll introduce the presenters as they go, and then we'll have our questions for all of them together at the end. So first of all, I will introduce our first speaker, which is Mika Pearce. She is with the Bureau of Meteorology, and she's part of the Bureau's high impact weather team. So she specialises in bushfire case studies and normally has the most amazing videos. And she does a lot of the fire and atmospheric modelling with Access Fire Model. She provides critical briefings to stakeholders during fire events, and is a wonderful person to work with in a fire operations centre. So I'll hand it over to you, Mika.
Thank you, Mel, for that lovely introduction. Can you hear me? Yes, can you hear me, and can you see my screen?
Yeah, perfectly.
You can see the screen? Excellent. All right. So as Mel said, I work at the Bureau of Meteorology, and tonight I think, there's so much that we could talk about, but I thought I'd do a little bit of an introduction into what we do with fire weather at the Bureau, and then show some of the case studies, because I tend to talk fast and then you'll have lots of images to remember afterwards. And English obviously is my only language, and I'm very conscious that for others, you're listening in second language. So we've been working for a long time with the fire agencies. This image here is actually the Conjola fire, which is one of the case studies that we've got running at the moment with RFS. And this was during the Black Summer that Mel just mentioned. But I think it's also interesting to note that this isn't one of our images. This is actually one of your images, because it was from the Copernicus satellite. So it just goes to highlight what Fabio was saying earlier about it really being a global problem, and there are global sort of approaches to it, because we're looking at your data at the same time we're managing our own fires and doing case studies on them. All right, so what do we do in the Bureau of Meteorology in terms of fire weather? Just a relatively brief overview. We are the National Meteorology and Climate Agency in Australia. So as Mel said, the fire agencies are largely state-based. And when we say fire agencies, we tend to mean the fire agencies and the land management agencies as well. And in a number of states, they've got multiple agencies. So from a Met perspective, we're a national organisation. But when we're working in partnership with fire agencies, we're actually dealing with multiple jurisdictions and multiple states simultaneously. It was interesting to look at the history, and there's a lot of history with the Bureau and the fire agencies working together since at least the early to mid-1900s in both the research and an operational setting. So there's a really long history behind the relationship between the agencies, and also all of that obviously has got us to the point that we're at today. In operations, we have specialist fire meteorologists at the Bureau, a very significant team of them. I think there's about 15, 20 in the team. And they specialise in doing the fire danger ratings and the briefing, and the location forecasts on an ongoing basis. So we don't have general meteorologists doing the fire forecasts. We've got specialist fire meteorologists. And their two main tasks are doing the district ratings for AFDRS. So it's a huge amount of work that goes into preparing the weather grids for AFDRS, and John's going to talk more about AFDRS later. And we also do seasonal outlooks, and we're one of the few places in the world where we're not just doing daily outlooks, but also doing seasonal outlooks to months ahead for how the season's looking and how it's shaping up. And that a lot of that is actually dependent on the rainfall data, because obviously that determines the vegetation growth and the fuel availability. And both of those are national gridded systems. So when we're doing those operational products, that's across the entire nation, obviously an area nearly as big as Europe, as Mel said. We also do a lot of location forecasts for going fires. So when there's a going fire, whether it's a bushfire, wildfire, or a planned burn or a prescribed fire, the agencies can call in and actually request a site-specific forecast for that fire. And we tend to do a lot of them. We did a huge number in Black Summer. On a typical day, on a typical bad day in summer, we might have a couple of dozen fire incident forecast going, and we usually do hundreds in a season, and this is across the whole country. So any significant fire will get its own forecast here in Australia. We also have embedded METs, as Mel mentioned, and these are in the fire agencies and the land management agencies around the country. So this is a bureau meteorologist, so one of our people who's working embedded in the fire agencies on a daily basis. And a lot of what we do is briefings, a lot of real-time interpretation, particularly working closely with the F-band teams. But importantly, those embedded METs have a direct data link back to the operational systems in the Bureau. So we've got access to all of the data and all the information in their agency that we would if we were sitting in our own agency. And that photograph below, that's a photo during Black Summer. That's the same room that Mel showed up on the screen earlier. And there's Simon standing in there behind me as I'm briefing the Premier and the Commissioner. We also do a lot of research with the fire agencies, looking at things like weather inputs to fire predictions, which comes back to AFDRS, also looking at a range of operational tools that we have, including satellite and radar, and a lot of case studies and 3D processes in the atmosphere. So, as I said, this is decades of collaboration, which has got us to the point that we're at the moment. But I just wanted to run through a few of the projects that we've been working on in the last few years. And these are projects that my team in high impact weather have been working on with the fire agencies around Australia. AFDRS is obviously one of those, but I think John's going to go into that in more detail. So a couple of years ago, we had a mobile radar that we took to Western Australia. And the reason we took it to Western Australia is that down in the southwest, they tend to do a lot of pretty big planned burns. So it was a good opportunity to take a radar because we knew that we'd have something to point it at. And this was a field campaign that was done in collaboration with the fire and the land management agencies over there. And you can see the radar. I've got my laser pointer. You can see the radar up here in the top corner. It was on a trailer which was attached to the back of a truck, and they towed it around the southwest and usually parked a few kilometres away from the fire so they could actually get nice scans of the plume. Now, the reason that we were using a mobile radar, if you look at this plot on the left here, you can see on the bottom here, that's what an operational radar, one of our normal operational network, would look like at 100 kilometres away from the fire plume. What an operational radar would look at 50 kilometres away from a fire plume. And this is the mobile radar resolution a couple of kilometres away from the fire plume. So obviously we get a huge amount of detail about what's going on in the plume. And that's an environment where it's really difficult to get observations of and also run models at that resolution. So really useful data sets to have. And one of the really important things isn't just what we get back in terms of the reflectivity information, because it'll tell us what kind of particles are in the plume. It doesn't usually pick up smoke, but you get ice particles and embers in there. But we can also look at the velocity signal. And it's really difficult and really interesting to look at the velocity signal in a plume from a radar, because you can see the inflows and the outflows at different levels. And you can also sometimes see vortices and rotation. And we'll come back a little bit later as to why looking at vortices is really important. Now, one of the reasons we want to look at what's happening in a fire plume is because of ember transport and spot fires, because spot fires here in Australia are a really key process in fire spread. And you may be aware the longest spots that we had during the Black Saturday fires were around about 34 kilometres. So they can spot and start new fires well ahead of the main fire front. These are large eddy simulations that a colleague of mine, Will Thurston, did a few years ago. And he used the model to try and unpack what some of the processes were that were happening in the plume, particularly in terms of the turbulence, and also what the landing distribution of the embers might look like. And we learned a lot of really interesting and really important things about ember transport and some of the processes that are important, important to capture when you're looking at doing any kind of prediction. But these simulations took ages and a lot of power on a supercomputer, so they were just much too slow for real time. So the next part of the problem was, can we compute ember transport fast enough for real time? So these are simulations that Jeff Keppert did, another colleague of mine. And what he did was he actually designed did the mathematics behind the ember transport parameterization scheme and put it into Spark, which I think Simon's going to mention later, which is our national fire simulator. So these are simulations that Jeff did of the Black Saturday fires, the 2009 Kilmore East fire. Let's see if I can just start it again. Is it going to let me? No, we'll try a different way. We'll try and get it started again. And some of the ingredients that Jeff had to put into the ember transport model included the time mean plume, the turbulence in the plume, the ember transport in the plume, and also the ember transport below the plume. You also need to know when and where the embers are generated, what the boundary layer structure is, so how high in the plume the embers are going to move, also what the winds are above the surface, because you want to know how far downstream the embers are going to get transported, and also what the burnout time is of the embers, whether it's a couple of minutes or whether it's 20 minutes, because obviously that would determine whether or not you've actually got a burning ember when it hits the ground further downstream. And as I mentioned, this is now in the operational version of our National Fire Simulator, Spark. So we've got to the point that we've got a useful operational tool, and that's driven by our NWP grids. Now, getting back to the question of why is it important to get ember transport into a model, particularly into a simulator, you can see here the difference in the simulations that Jeff did without spots on the left and with spots on the right, which was actually a very good match for the actual final fire perimeter. So particularly when you're talking about the eucalyptus fuels, and particularly some of the ones in southeastern Australia, it was really important to get that ember transport into your modelling in order to make it accurate in real time. Another piece of work that the team's been working on, Kevin Torrey has developed the pyrocumulonimbus firepower threshold. And this is really in response to the Canberra event, which was nearly 20 years ago now, where there was a pyrocumulonimbus and a pyro tornado in the Canberra suburbs. And since then, there's been a huge amount of effort across individuals and institutions, not only in Australia, but also in the States as well. But we're now at the point that we've got national predictive capability, which has got really useful skill. So what Kevin did was he tried to work out what are the ingredients that we need to think about from a thermodynamic perspective using an aerological diagram. And we'll just kind of gloss over the maths for those who are interested, but we'll get a little bit into the visualisations in a sec. But effectively, what you want to know is what's the saturation point curve and the potential temperature of the mixed layer of the atmosphere, as well as the moisture levels, so the mixing ratio in that mixed layer. And that will tell you what the lifting condensation level is, the level at which cloud will form. Now, in this case, it's too dry above the lifting condensation level to get cloud to form. But if we increment that, we'll actually find out for this atmosphere what's the free convection theta E. So what temperature do you need to get free convection? And that will tell you the the level of free convection, and then what the plume potential temperature needs to be in order to get to the level of free convection for this particular atmosphere. And what you can then work out is what the delta theta is. And the delta theta is the increment in temperature, which can also be thought of as the energy that's needed from the fire plume to get a parcel of air to that level of free convection. Now, when you look at the equation here on the left, you can see that we've got a constant in here. We've got our level of free convection, which we can get from an atmospheric model or from an observation. Same again, we've got our wind speed through the layer, which we can get from our observations or from a model, and the delta theta, which can be calculated. So what Kevin's then done is being able to map out from our NWP models a whole set of different plots. This one that we're looking at here is the PFT flag, which is the pyrocumulonimbus firepower threshold in gridded form with the VESTA model. So what is the potential for fire spread? Because it's not only could you get a pyro CV, but also are you going to get a fire that's big enough and moving fast enough to generate enough energy to create a pyro CV in that environment. And what we've got here is the Sarah Ivan fire. I think Mel showed a photograph of this one earlier, which produced a really short-lived pyro CV on a frontal wind change. And that favourable environment, which was quite transient, was identified in the PFT flag. So since this event, we've had a number of events where the PFT has been shown to be really successful. And as I mentioned, anywhere that you've got NWP grids, you can calculate the PFT and the other components of the model. So this is obviously over Europe. Kevin's been working with the people in Canada at the moment, and they've had quite a lot of success in the PFT flag identifying events in the recent fires that they've had there. And I know that he's working at the moment with a few people in Europe. It's kind of complicated and requires a fair bit of training to be able to use it effectively, but has turned out to be an incredibly powerful tool in looking at the potential for fire-generated thunderstorms. So another project that we've been working on for quite a while now is Access Fire, which is our coupled fire atmosphere model. So it's similar to those who might know WRF Fire or the MESO NH4 fire model. This fire spread model is coupled to the Access numerical weather prediction system, which runs in the land surface scheme of the UK Met Office unified model. So it's the UK model with a fire component plugged in underneath it. It captures the fire-modified winds and also deep moist convection, but at the moment it doesn't have any smoke or chemistry transport in there. So that's something that we could add in future, but we haven't at the moment. When we run it, we usually do it in nested domains down to 300 metres or sometimes to 100 metres. I'll show both in the subsequent slides. And the fire for these runs on the innermost nest with 140 vertical levels. And we can either initialise the fire from a point ignition or from a fire perimeter, and we've done that from line scans that RFS have provided to us. Importantly, it's consistent with the operational Spark and AFDRS fuel grids and fire spread models. So we've got quite a lot of coherence now across the various systems that we're using operationally in Australia. So far, it has been computationally expensive, so it's not really imminently going to transition into operations, and we're just using it for research. But this little schematic shows how it works. We've got the atmospheric model, which runs for a time step. It then feeds surface parameters, mainly the main ones are wind and temperature, to the fire spread model. The fire spread model takes those inputs, runs for a time step, calculates heat and moisture fluxes from the amount of fuel that's consumed, and feeds those back into the atmospheric model. So at the next time step, the atmosphere knows that there's a fire underneath it emitting an energy flux, and the winds change in response. So looking at some simulations from it, and this first one is, firstly I just wanted to show a few with sea breezes. So this is the Yanchep fire. This was a fire in Western Australia. We're looking just north of Perth at the moment in Western Australia. This was back in 2019. And this fire ran for 3 days, and it effectively zigzagged up the coast because we had easterly winds for most of the period, particularly during the mornings and the overnight. And then the really strong Western Australian southwest sea breeze came in the afternoon. Conditions were really hot and dry, which meant that suppression was really difficult overnight. And despite the fact that they had 180 odd firefighters plus aerial support on, the fire continued to run for 3 days. But what's really interesting in the simulations you can see here is the fire perimeter response to the changing wind regime as the easterlies and the sea breeze were kind of oscillating between the two cycles. I think it's just about to start again. So the initial fire you've got, you can see how it firstly runs on the head fire. You can see the sea breeze approaching, and the sea breeze starts to change the direction of fire spread to the north. Then for a while, the fire's actually trapped in between the sea breeze and the easterly, so you don't get a lot of fire activity. And then as the sea breeze dies down into the evening, that flank of the fire becomes much more active as the easterlies start to dominate. So it's a really interesting example of how when you're looking at winds at a point, they're not necessarily going to tell you the whole story of how a fire perimeter is experiencing a sea breeze. Now, to look at another real-world example of the same kind of processes, again, this is in Western Australia, but this time we're looking at the north of Australia, and we're seeing this in the real data in Himawari. And what we're looking at here is the hot spots when there were a number of fires, very large fires burning in the area. But what you can see is as the sea breeze comes in the evening, and up in Western Australia, we get these sea breezes that tend to penetrate really strongly inland in the evening. You can see how the hot spots on the fire perimeter shift in response to the sea breeze. So obviously for sea breezes, when we start to see sea breezes, we're really thinking about the processes and the different wind regimes that are driving them. Another maritime example, not a sea breeze in this case, but this was the Kangaroo Island fires in January 2020, when most of the island burned. A lot of it was on the 3rd of January, which is the day that we're looking at here. So you can see we had a really hot fire up in the western side of the island, but the area of interest is underneath a little bit of cloud down the bottom corner here. There's a lighthouse, quite a famous lighthouse. It's heritage listed at Cape de Koodi. And amazingly, although most of the west of the island was burned, the Cape de Koodi lighthouse and its cottages were untouched. And when you look at this, again, really high resolution satellite image, you can see just down in the bottom corner here, there's a little green patch on that corner where the lighthouse and the cottages are placed. And when we ran the high resolution simulations, you can see that there was turning of the winds that turned the winds through that area. And this continued for several hours through the afternoon. And part of the reason for this is that during the day, the land surface temperature was really hot. Even without a fire, it was getting up probably around about 40 degrees. And the sea surface temperature, because that's the Southern Ocean, there's nothing between there and Antarctica. The sea surface temperature is only in the high teens at best. So you've got this massive temperature contrast between the land and the sea and this little promontory. And what that caused is the winds to turn through that area, which held the fire off the lighthouse and the lighthouse cottages. But without having that high resolution modelling and being able to think about what the processes are at a local scale, we're not going to see what the mechanisms were for the lighthouses not being burned. So another case study, this is one that we did of the Corryong fire. So we're looking at Victorian fire at the moment. This fire made a 36-kilometre run overnight. This was on the night going into New Year's Eve in the 2019-2020 season. What we're looking at here, the bottom corner here, we've got the fire perimeter in red. The black line here is the cross-section, and the cross-section is showing, if I can just get it to run again. No, it doesn't want to run again. Try again. So what we're seeing in the cross section is that animating for you guys? I think it's stuck.
It had started and then it stopped again.
I know, it's annoying, isn't it? Technology. And we've been using this one for ages. Okay, there we go. So you can see the cross-section here. What we're looking at is the winds above the surface. So this is wind speed above the surface going up to 9 kilometres. And you can see that the focus of the winds is in the lowest 1 to 2 kilometres, which is actually less than 1 to 2 kilometres above the topography. So it's probably mostly around about a kilometre above the topography. And those wind speeds are getting up to 70 to 80 kilometres an hour. Now, the question was, why were those wind speeds above the surface driving that fire activity to run 36 kilometres in the overnight period? And it was because of the fire and atmosphere interactions and the interaction between the winds above the surface and the fire plume. Now, with the coupled fire atmosphere model, we can run it with fire coupling off and with fire coupling on. So we can see how the atmosphere is going to respond without a fire there and with a fire there. So what we're looking at here is a close-up just of one time step. And you can see that without a fire, you've got the low-level inversion forming, you've got the separation, as you'd expect, between the winds above the surface and the surface winds during the overnight period. But when we've got a fire plume in the environment, that fire plume is pulling down or mixing down that low-level jet down to the surface, causing an overnight fire run. So now we, on a regular basis, have our forecasters looking above the surface for these low-level jets, not just during the day, but also in the overnight period, particularly when there are heavy fuel loads, to say, okay, is there any potential for the winds above the surface to affect this fire in the overnight period? Another one that we looked at was the Green Valley Fire. This was one that RFS asked us to look at in detail after the Black Summer fires, and it's because a young RFS firefighter was killed when a fire truck was overturned by a fire-generated tornadic vortex. So this is effectively a fire whirl with tornado-strength winds. And you can see a couple of different processes here in rotating phenomenon. On the right here, we've got the entire convection column above the fire rotating quite slowly and over a large spatial scale. Underneath this rotating convection column, this fire-generated tornadic vortex, which is around about 60 metres wide, emerged and moved ahead of the main fire front, and that was the fire vortex, the fire-generated tornadic vortex that overturned the fire truck. So following this, we've done a lot of research on these vortices to find out what the drivers are, but also to try and understand what the ingredients are that discriminate between a small fire whirl and a fire-generated vortex, which has got wind speeds up around the 300 kilometre an hour mark or even stronger. So we ran simulations with the coupled model. When you've got a vortex forming, there are two things you need. You need a spin component and a stretch component. And when we looked at the time series from the coupled model at really short intervals, it showed a really transient pulse of up motion over the location of the FGTV at around about the right time. So on the left plot here, we've got the stretch component is effectively the fire's updraft. So we've got the fire perimeter in red, the background winds in black, and these red areas are showing us really strong up motion. The middle plot here is showing us a cross-section of those two pulses on the flanks of the fire at the time the vortex formed. So you've got really strong up motion up to around about 4 or 5 kilometres above the fire. And we've also got a lot of low-level vorticity, so a lot of rotation, whether it's horizontal vorticity or vertical vorticity or a combination of both around the fire ground. So you can see that with the fire-modified winds around that fire front, you've got lots of local areas where you've got a lot of vorticity sitting in there. And we can also, again, look at this in other data sets. So if we look at the satellite image, we can see really rapidly developing towering Q in there. But when we start to look at the other channels that are available, this is the Himawari 13 brightness temperature, you can see that in the cloud top temperatures, there was really rapid growth from around about minus 10 degrees C to minus 20 degrees C. So really rapid vertical motion right above the fire at the same time the vortex developed. So we've got lots of different data sets that can help us develop the story and the narrative of what happened with the case. And we can also start to look for some of these ingredients in future events. So the last case study I wanted to talk about was the Currowan fire that we touched on in the beginning. This was on New Year's Eve in December 2019. And there were 3 fatalities at Lake Conjola and Conjola Park when the Currowan fire jumped the Princes Highway, so 6-lane highway, spotted across the highway and burned towards the coast. But importantly, the local fire behaviour in this environment really didn't reconcile with either the forecasts or the observations. So this was a line scan image, this top plot is a line scan image that was taken around about 10 o'clock in the morning, and you can see the fire area. And then at midday on the satellite image, we can see just how much that fire area had expanded. And you can see the spots on the other side of the highway in through here. So we're running a case study to try and understand what some of the drivers were. Now, when we look at what happened, we've got the AWS plots, the automatic weather station plots on the left here. When we look at both of the nearby automatic weather stations, they're really not reflective of the local conditions and really different at the coastal site and at the inland site. But when we look at the access fire simulations, you can see that there was really, really strong northwesterly winds in the morning, and then this really strong coastal surge that came up and changed the direction of the fire front. But we can see that local variability in the area over the high ground and over the lower ground, and then the surge as it came through. So by running this at 300 metre resolution, we get a lot more detail in the wind variability. But we can also, again, look at vertical cross-sections of what was happening in the plume. So this is a cross-section, if you can see, through the fire perimeter in this little inset plot. What we did find is the maximum plume height was a really good match for the radar observations that we had. But when we look at the cross-section of the plume, we can see the plume really, really strongly tilted downwind in those northwesterly winds. We can see it getting up through the top of the mix layer and producing cloud, and we've got precipitation processes which are resolved in the modelling framework. But we can also see this density current. This is our sea breeze, our frontal change that's coming in off the ocean here. Much cooler air in the density current. In the next couple of time steps, that density current cuts off the plume. And that was when the cloud started to move downwind as well. So we're getting all of these different processes in the satellite imagery, in the radar imagery, and also in the coupled fire atmosphere model. And that helps us identify the kinds of ingredients that we can look at next time in future events. So just to summarise, there's decades of research and operations in the fire agencies all the way across the country, and with the Bureau of Meteorology as a Commonwealth agency. And we've been collaborating on research projects and also during real-time events for planned burns and for wildfires for many, many years. A lot of what we've been doing in my team, in the high impact weather team, is looking at the three-dimensional structure of the atmosphere, so not just what's happening at the surface, but what's happening above the surface, with a range of different tools that we've got and modelling frameworks that we've got, including the coupled fire atmosphere simulations, and really trying to look at what's happening with the fire modified winds and also the pyroconvective cloud, because those are things that tend to be really important in real time in terms of how the processes are actually unfolding. And a lot of what we see is it's about local detail in the meteorology that's driving the fire behaviour. So if you look at a broad scale grid, you're going to be missing some of the detail, but a lot of the time it's really drilling down to quite fine scale processes, and also looking at the fire atmosphere interactions as well, and remembering that the atmosphere isn't unmodified when you get a large fire in there. Thank you.
Thank you very much, Mika. I've seen quite a lot of that before, and I will be waiting for the recording because there's a whole lot of that I'd love to show my team. I think it's really incredible work. It's so interesting, and I'm sure when we get to the end there'll be lots of questions. I might just say, if you want to put your questions into the chat, I'm happy to work off those if you want to pop them in now, and then we can ask them later. We'll move on to our next presenter. So John will be presenting next. So John Runcie leads the team looking at part of the fire danger ratings system. So while his job title says he works for New South Wales Rural Fire Service, and he has been a really long-term volunteer with the organisation, and he's put on here, he does on his bio has the RAF, so the remote area, but I also think he's got the really cool role of with the trail bikes as well. And he's been working in this team since 2018, and a really great showcase of a national project that we're very proud to have embedded within our team in New South Wales. So take it away, John.
Great, thanks, Mel. That's a really glowing introduction. Thank you. So the Australian Fire Danger Rating System has been going for a while. And I'll give you a bit of background. So how did we get to where we are now? We used to have a fire danger rating system of sorts, but in 2009, we had some very severe bushfires or wildfires, and they were a catalyst for change. So we had very hot and very dry conditions, and they preceded a severe heat wave and those very strong winds, multiple ignitions, and we ended up having 173 fatalities during those bushfires. The Prime Minister said, "This is a tragedy beyond belief, beyond precedent, and beyond words." And in one of the darkest days in Australia's peacetime history, it was a dramatic event that made us all stop and think. Were we prepared? Were we did what was going to happen? So fires are increasingly being experienced beyond the intended design limits, especially of the older fire danger rating products that we used to use. We used to use the Forest Fire Danger Index and the Grass Fire Danger Index. These two indices were derived from empirical fire observations in the 1960s. The difficulty in these indices accurately representing fire danger, therefore, it makes it challenging to communicate the risk to the community at the higher end of the scale. So that large bushfire in 2009, or that series of bushfires, were pretty much off the scale of the fire danger rating model, fire danger ratings that we use, and models from which those ratings were derived. Now, we also found that the old system wasn't able to make use of improved weather, satellite, and fuel information. So there's a number of issues which we found with the older system, and was recognised that we needed to do better. The community was confused by the old system due to too many levels, colours, names, and inconsistencies. If you look on the left, you can see the image where there's 1, 2, 3, 4, 5, 6 different levels, but now we've got 4, and we've found from social research that 4 is much more well received by the community. Something simple for them to understand is much better. So a new system was needed. The 2009 bushfires provided the impetus, and so the AFDRS was initiated. And it's taken over 10 years for us to get to the point now where we're actually using this system. So what we wanted was a national system that benefits everyone. And we wanted a system that was designed on the latest science and the latest data that's available, and all the sort of data that Mika talked about that the Bureau's able to provide now. We wanted to incorporate all those good new things. It needed to be continuously updatable and modular, and it was set up so that it was set up in a way of collaborating between all the agencies and the Bureau. And so there's been a lot of interaction between individuals and organisations across the country to get this system set up. So the points I've got here, it's a modular and designed to have the capability to adapt with better information and technology. So we can put models in and out as we go. The idea of the Australian Fire Danger Rating System is to provide better decision-making tools and improve the way that fire danger itself is communicated, leading to more resilient communities, ecosystems, and economies. So it has that overall longer-term, broad impact on the community. So there was quite a significant community engagement and messaging effort when the AFDRS was implemented and sent out. That was funded by the government, and there was a bunch of different things here. There was TV and radio commercials, digital print and billboard assets, radio ads. We also had a lot of different ads in different languages. You can see in the centre lower, quite a lot of different languages. Fact sheets were available in 10 different languages. And there was a guidance translated to a further 25 languages. The settlement guide was designed to assist migrants in Australia with practical multilingual information. So we were targeting not only people who knew about fires, but people who had come into the country who had no clue about fires. And we have a lot of migration into Australia, and we have had over the number of decades. So it's important for us to ensure that all citizens and residents are aware of the danger of fires. Okay. So we have the old system on the left, and we have two components to the new system, the AFDRS. On the top, we have the fire danger ratings. So we've got those 4 levels. The broad categories are designed to quickly communicate to the public the potential level of fire danger. So moderate, high, extreme, catastrophic, as opposed to the somewhat ambiguous model on the left, which was different between states. So one of the key things with the Australian Fire Danger Rating System is that now we have a national system which is consistent around the whole country. So if I go to Perth and I look at the AFDRS, I'll understand it. I don't have to relearn some new system. And that's quite a significant, it's a subtle change, but it's quite significant. On the lower right, we have the Fire Behaviour Index. This is a numerical index. And that's specifically designed for operational users and fire management decision making. So a lot of us here now today would be interested in the Fire Behaviour Index, maybe more so than the fire danger ratings, which are more general. So the Fire Behaviour Index is a scale of fire danger that produces outputs across 8 different fuel types, and we'll come to that in a moment. The scale is similar to the current system. The scale of both systems is similar, but they're not directly comparable. That's fine. So national tool, public safety, clear actionable information on wildfire danger. So some key features, and it was important for us to design this system, not only for operational people such as ourselves here in this webinar, but also the community, the people on the street. We have these signs up around the country. On the side of the road, these signs are everywhere. And so people need to understand what they mean. In the old days, perhaps people would pay less attention to these signs, but since we've had a strong community outreach effort, more people are aware of these signs and more people understand what these signs mean. For example, a benchmarking survey in New South Wales found that 93% of people agree that they are confident in taking action. 90% believe the new ratings gave clearer actions to take, and 95% believe the new ratings are simpler. So there were a bunch of positive results that came out of surveys post release of the AFDRS to the public. All right. So this example is for forest fuels, and you can see here we've got on the top we've got the ratings. So the ranges of the index itself from 0 to 6, 6 to 12, 12 to 24, and so all those purple colours on the left are the moderate. If I just jump back a step, I can show you. Well, and then high. This one here is a yellow, and extreme and catastrophic. So the cool colours represent conditions where fires are unlikely to spread. Conditions increase to support a spreading, self-sustaining fire, mid-purple. And then the range of conditions in this category also aimed at representing typical prescribed burning conditions. And so for operators in the field who are doing prescribed burns, these ratings can be quite helpful. A step upwards in conditions where prescribed burning is generally no longer suitable is from 24 up into the 24 to 50. The warm colours, the transition is linked to a change in suppression response. And so you're typically moving away from offensive suppression success and increasingly into defensive strategies. And the final two categories, the 50 to 100 and the 100 plus, they're set based on increasing likelihood of community losses, more specifically houses and potentially lives. So you can see that the ratings themselves have particular messages associated with them. And these translate back to very simple messages to the community. And they also translate messages for us as operators. So how does it work? In the last 10 to 20 years, we've expanded our understanding of fire spread and fire behaviour into 8, and we've used 8 broad fuel vegetation types to describe fire in Australia. And these are the papers and the models that we've used. We've modified them to some extent, especially recently. With these additional fire spread models, we're able to consider a whole new range of fuel types. So initially the system worked in grass and forest and forest. But now we've got these 8 different primary models and then lots of submodels. We've recently updated the spinifex, snowy heath and pine models, partly in response to field observations of original model performance. And so here's an example of different fuel types. So the AFDRS works at a 1.5 by 1.5 K kilometre grid scale. And you can see those dots on the left. That's primarily Victoria and southern New South Wales. And there's a whole bunch of different fuels there, so way more than 8. So the dominant fuel in each cell, this is how it works. The dominant fuel in each cell decides which fire behaviour model to use. So if the dominant fuel is grass, then it's a grassland fire behaviour model. So weather inputs such as wind speed, humidity, and are included, and fuel data is used. And then we use those information to calculate the rate of spread and fire line intensity. So ultimately, the fire behaviour index is derived from either the rate of spread or fire line intensity. Fire line intensity including information about the fuel itself. Yeah. Okay. So I'm rushing through all this. I'll send a link at the end, and you can go on the website and look up all the details. But what I wanted to do is provide you a bit of background and a bit of a broad understanding of how the system works. This is probably the most detailed slide here. Here's an example of the grass model and how it's changed from the MacArthur Grass Fire Danger Index, the GFDI, to the AFDRS Grassland Fire Behaviour Model. You can see the GFDI increasing with wind speed. So that's this center lower panel here. And then and you can see the different colors representing the different ratings. So there's 5 different ratings there. But on the right here, you see the AFDRS here, and it's a different, but it's similar. We've got four ratings instead of 5, but we're looking at rate of spread as a metric. Now the schematic on the top right shows the different inputs that go into the grassland AFDRS model, which includes a number of different fuel components. So fuel condition, curing, the continuity of the fuel, and actually the amount of fuel. And these inputs are far more than the old GFDI. So there's distinctions between the two, and essentially we're using better models. This one here, this is about some of the detail we go into to actually get data that informs the modelling. So grass changes so quickly. So we actually have in the country people who go out and measure grass and report back on grass condition and loading. And for example, here on the bottom left, you can see natural grasses where there's quite a lot of biomass, grazed where there's far less, and eaten out where there's hardly any biomass. And so these tonnages, if you like, of fuel go into the models, and the models spit out a danger rating appropriate for the amount of fuel. So if you look at the eaten out on the bottom right, then the danger that would come out of that would be far less than that on the far left, natural. So that's a very simplistic way of looking at it. So outputs. So there's a fuel state editor. There's three operational tools that come out of this in particular that are useful. There's a fuel state editor, which is an interactive tool that allows fire and land management agencies to capture field information, and they can update their maps and then export them to the fire danger calculation engine. So people can go into the system and change the data that they will be ultimately using in their state. Obviously, those people need to be verified, so we don't give that to everyone. That's quite an important aspect because we're not able to update everything in the whole country because it's so big. So we've given people the license to do that. The fire danger calculation engine, which is seated within the bureau where Mika works, combines the various fire behaviour models and calculates the fire behaviour index. And then there's the fire danger viewer, which is an interactive tool which FBANs can use, so fire behaviour analysts and operational people. They're very useful. And you can see various images that come out. So this one on the top right, there's a rough isochrones of the fire, and the pixels are telling us what the fire danger rating is. So you can see it's orange. It's 50 to 99, which is very high. Well, actually, that's extreme, literally extreme. And if you look on the bottom right, extreme 77, extreme 84 on the Sunday in the Mallee and the Wimmera. And so that's another way of getting the information out of the AFDRS. So the Australian Fire Danger Rating System is built with a vision for continuous growth and enhancement. It's designed to mature over time and remains a stable and reliable system. And it's able to adapt to new research findings, technological advancements. We have a commitment to ongoing improvement, so it means that the AFDRS will evolve in response to feedback and incorporate the latest developments in fire behaviour science. So this dedication is central to our goal of providing better protection for our communities, reducing the loss of lives and minimising property damage. That's the rationale for this. And very briefly, just a few minutes, I'll just give you a bit of an update on what we're doing at the moment. So in 2022, we released the AFDRS to the public and to operational people. And for the last few years, we've been studying and improving various parts of the system, and working quite closely with people around the country. But we've also been developing 3 other indices which were recognised when the project was initiated 10 years ago. So we've got an ignition index, which forecasts the likelihood and an ease of ignition from natural and human sources, a suppression index, which forecasts the likelihood of initial attack suppression success, and an impact index, which forecasts the likelihood of impact on assets. And actually, a paper describing our impact model recently accepted for publication in the International Journal of Wildland Fire. So that's really nice. So that'll be out pretty shortly. We'll submit that tomorrow morning. So that's hot off the press. So like I said, I won't take very long. I can see Melissa's looking at me. Very briefly, we ran a bunch of workshops this year. So for the first 6 months of this year, we ran 3 sets of workshops. And the intention was to talk to all the people who use this system and to see what they thought about these fire indices, these ignition, suppression, and impact indices and related products. And from those user requirements workshops, follow-up workshop, and subject matter expert workshop, we've come up with a shortlist of products which we would be providing to those 3 indices. And we travelled around the country meeting with people, which was actually really good. So you can see a whole bunch of user requirements there. I won't read them out. But on the left, for the 3 indices, the uppermost comment is the highest priority. So for the ignition index, a flammability index was considered to be the highest priority. And then real-time lightning strike data was the second priority. So people are interested in that, but the flammability index was the highest. In suppression index was the highest. And in impact, just knowing where valued assets was going to be the most important thing. So we're all done. And here's the flammability index, just a rough one. So you can see how the color changes on the top right. And the flammability generally increases if you go further inland. Here we've got temperature and we've got the spots in care facilities. And so you can see that those aged care facilities up in the top right of Queensland are high risk. You don't want aged people undergoing heat stress. Time since fire layer, which is useful for all of the AFDRS. So we've got color coded here, just the north. And you can see actually since the red, there's very frequent fires in the north every year. So it grows quickly and it burns. Suppression index, you can see here, getting into some of these national park areas, very difficult to access. So suppression is pretty unlikely within your probability of initial attack success is pretty unlikely. Key benefits. New indices underpinned by current science provide more nuanced, robust predictions of risk, nationally coordinated, national preparedness for and response to wildfires, significant cost savings expected. Introducing the AFDRS gave us an example of what's possible. So it's the first national collaboration of this scale across Australia's emergency management landscape. So it's quite a significant and new thing to do, and it's being and it's in a position where we can continually update and improve it, and that's what we intend to do. So thank you.
Thanks, John. I'm glad you mentioned the workshops, because I think that's a really key part of, I guess, some of the success of research into operations, is that it takes a lot of time and needs to listen. And I know how tired that team was, because they sit nearby, and just going around the state and going to so many different workshops. I think the summary is, if you come to travel in Australia, particularly in summer, you can travel anywhere in the country, and you know that you'll be able to get a good measure on what the fire danger is based off the signs on the side of the road, but also the huge amount of science that underpins that. So yeah, if you want to come for a holiday, or even better still, come over and help us out as a fire behaviour analyst or any other sort of role, you know that you've got a lot of tools there to help support you. We'll pass on to our next presenter, which is Jason Sharples. So Jason is a mathematical scientist and the founder of the foundation director of the UNSW Bushfire Group. One of my first recollections of Jason was I met him at a modelling and simulation conference, which was my fault for being there, but I really didn't understand much of what he said. I feel like we've come together so much closer now. I'd like to think that I understand his work better, but I think I now see him in more appropriate audiences. So from his very strong mathematical brain, he is a really great contributor to fire science and policy within Australia. So reading the rest of his bio, he's a global expert in dynamic wildfire behaviour, and his research uses advanced models to understand extreme wildfire propagation. And yeah, as I said, he works helps out in an operational sense, but also very strongly on that policy side. So I'll pass it over to you, Jason.
Mute is off. Yep, it's not the right one. You want the other end of it. All right, good to go? Okay, well, thanks, Mel, for the introduction. And thanks also to Fabio and Pau Costa Foundation for the invitation and opportunity to talk to you. So what I was going to talk about, it says there, I'm going to talk about some of the operational implications that arise when you start to consider the possibility of dynamic fire behaviours being involved. So really what I'm going to be talking about is a particular form of dynamic fire behaviour, one that we've been studying, best part of 20 years now. It's not only us, we've had great help from the team in Portugal, from ADAI, the University of Coimbra, and it's been a bit of a global effort with lots of other people involved in various ways as well. But what I thought I'd do to try and, I guess, illustrate some of the operational implications is really just go through a bit of a hypothetical scenario. So just going to sort of set up a possible scenario for a fire burning this terrain, and you can see that the key feature here is it's fairly rugged terrain. So let's just suppose in this sort of landscape, we've had a fire which is detected on a Friday afternoon around about 3 p.m. Conditions are hot and dry, and we've got some moderate winds coming out of the southwest. You can see there with the blue arrow. So people are responding to this fire, and one of the first things they do is they put in a retardant drop to the north of the fire to stop it progressing too far to the north under those southwesterly winds. The fire weather forecast for the next day, Saturday, has come in. Temperatures are hot. Relative humidity is getting dangerously low. We've got the winds moderate, 8 to 16 kilometres per hour out of the southwest, but they're forecast to shift to the west and to strengthen up to the order of sort of 18 to 30 kilometres an hour, with gusts up to 45 kilometres per hour. So not a good forecast if you're trying to suppress a fire. So in response to that, they can make a prediction on where they think the fire is going to go, and it's something like that you can see there. And so based on that prediction, the decision is made to put in some crews on that east-facing slope there and establish a hand line to be able to sort of contain the fire as it goes over that ridge and onto the leeward slope there. The wind change comes, that westerly wind strengthening, and the actual fire behaviour by the morning on Saturday actually looks like this. So everything sort of seems to have worked as it's done. The retardant line has held the fire, and the hand line that's been put in has held the fire for the most part, but just a small slop over that can be seen there. But we've got fire crews there working on it, trying to contain it. So what I want to do now is really sort of stop there and just think about two ways of looking at this problem. One will be sort of from a traditional quasi-steady approach to understanding fire behaviour, and the other one will be a more dynamic approach, and just sort of compare and contrast those two different ways of thinking about what might happen from this point. So first thing I want to do is talk about this sort of so-called traditional paradigm, or the quasi-steady paradigm. So, for example, a lot of the models that have been talked about, particularly those which underpin the Australian fire danger rating system, are quasi-steady models. So what I mean by this is they're models which have kind of been, which kind of produce a rate of spread function, which is uniquely defined given inputs like the wind and the fuel and temperature, relative humidity. So essentially, if you know what all those conditions, all those variables are, you put them into your quasi-steady model, and that will give you a rate of spread, or an estimated rate of spread. If those conditions aren't changing, then your rate of spread that's being estimated won't change either. So based on that sort of approach, the kind of guidance we'd be given by that is we've got a westerly wind blowing. It's sort of blowing over the leeward slope, so it may sort of be weakening. But what you'd really be expecting is the fire to spread towards the west, downslope, driven by that westerly wind. The crews on the north of the fire across the slope on its flank, and they're aware of the situation they're in, so they've identified 2 escape routes, as we're always told to do as firefighters. So the first one, they sort of said, well, if it starts going, we'll just sort of track along the flank and slowly move away from it, moving downhill so we can go more quickly. And the other one, which I suspect I would sort of advocate as the safer one, is just to move north away from the fire across slope, so you're still not really having to expend much energy going uphill. So go across slope away from the fire and put as much distance as you can between the fire and yourself as quickly as possible. Okay, and I've been in situations involving this sort of scenario, and this is the kind of a standard response. Take advantage of the downhill run, try and put in a hand line on the flank to contain it, but be aware of the potential for things to go wrong. And I guess it's really where the dynamic idea comes in, is sort of how things can go wrong changes depending on the way that whether you're considering a traditional sort of quasi-steady approach to understanding the fire behaviour, or a more dynamic approach, which I'll go into now. This is where the science comes in, though. So all about showing how the science is being used in making these operational decisions. So we'll sort of step aside and just do a little bit of science first before we come back to this this scenario. So I'll thank Mika for talking about vorticity, because I'm going to talk about it as well. What we've got here in this picture is a ridge line. You can sort of see there. Let's suppose that's sort of a north-south aligned ridge line. And we've got a westerly wind coming in from the windward direction. And if that ridge is sort of sharp enough or prominent enough, and if the slope on the lee is steep enough, then what happens is, instead of just flowing over the ridge, the flow will actually separate and then recurve back on itself, giving you this sort of vortex sort of motion here. The arrows are representing there. This is your classic separation eddy or lee slope eddy, lee eddies for short, which is kind of a very different situation to one you would get if the winds were, say, more from the southwest. They're not really aligned with that north-south ridge line. And so instead of separating and recurving, they tend to just flow up and over the terrain, like my badly drawn arrows are trying to indicate there. Okay, so no eddies in that situation. So very different dynamics in terms of the way the winds are going to behave over that leeward slope. With the winds coming from the west, you get these eddies. And what we tend to do when we talk about vorticity is we conceptualize it essentially as what we call a vortex tube. So we can sort of think of those arrows sort of forming this this tube of rotating air, if you like. It's an abstraction, but it's one which is kind of nice to illustrate the concepts. All right, so Mika also talked about these following concepts a little bit: vortex tilting and stretching. She talked about tilting and stretching in particular, but what we want to think about here is the way vorticity can be tilted, or vortices can be tilted. So suppose you've got a little vortex tube like I've shown there, and the arrows are indicating which way it's rotating. And let's just think about what happens if we hit that with some sort of updraft. Okay, this could be any sort of updraft, doesn't have to be from a fire, but a fire would be one such example of a thing which could produce such an updraft. What happens in that situation is the vortex tilts. Okay, now, because of the conservation of angular momentum, that tube sort of maintains a level of coherence. So it doesn't sort of just break up straight away. It tends to bend, like is depicted there. But at the same time, with the angular momentum being conserved, the spinning motion has to be conserved all the way along that tube. And if you sort of think about how it's spinning as you go along that tube, on the right there, you've sort of, if you're looking down from above, you've got this anti-clockwise rotation, whereas on the left, you've got a clockwise rotation. So by tilting this vortex, which was purely horizontal vorticity to begin with, you've now introduced vertical vorticity, but you've introduced vertical vorticity with opposite signs. So we call these counter-rotating vortices. Okay, and that's what tilting does for you. The other thing that can happen, and Mika already sort of talked about this, is if you've got some vorticity, just say in this little bit of tube here that I've shown, could be part of the bigger tube that you can see on the left. If it's spinning a certain way and you try and stretch it somehow, again, this could be due to the plume of a fire or some other force, angular momentum has to be conserved. So when you try and squeeze that out or stretch it out, it intensifies. So you get stronger vorticity, stronger spinning motion. And I think most people are familiar with, ice skaters, when they start doing a spin, if they have their arms out to begin with, as they bring their arms in, their rate of spin will increase. So it's the same sort of thing going on here, exactly the same thing. Okay, so vortex tilting and vortex stretching, two very important concepts when it comes to the dynamics of vorticity. So let's have a look at what that means for a fireground. And you can see here with my little cartoon, it can have some pretty significant consequences. So the picture we've got here, if we sort of start down the bottom, we've got some ambient horizontal vorticity which forms. Now, that could form a number of ways. It could form just due to the vertical shear being in the winds caused by the friction from the ground. So the speed closer to the ground is lower than the speed of the winds higher up, and that causes the wind to sort of overtake itself and form vorticity. Or it could be the vortex tube I showed you before forming in the lee side of that ridge. Okay, so let's just suppose we have some ambient horizontal vorticity somewhere in the landscape. What we're going to do now is we're going to put some fire into it. Okay, so the fire, as I said, will cause an updraft. And if that updraft interacts with that horizontal vorticity, it's going to tilt it. Okay, it's going to tilt it into these counter-rotating vortices. The fire's updraft is also going to stretch that vorticity, which is going to strengthen it. Okay, and this is kind of one of the classic ways that you can get firewells to form. So once the fire sort of gets involved with those different, those two counter-rotating vortices, you'll end up with the two counter-rotating vortices that you can see up there, up the top of the diagram at number 4. So that happens on flat ground, but it also happens, and it happens in a much more, I guess, coherent and consequential way when you get fire involved in the lee slope eddy. Okay, those eddies tend to be a lot, the ambient horizontal vorticity tends to be a lot stronger and a lot more coherent, and so the fire's plume is able to interact with it more strongly. That brings us to something we've called vorticity-driven lateral spread. So you've got a ridge there, which is the white dotted line. You've got some wind, which is coming across with making a certain angle with that ridge line. And we've got a fire, which is perhaps ignited on that leeward slope. We have horizontal vorticity over that slope, so the winds are recurving back. So instead of the fire burning with the wind, it's actually going to burn against the ambient winds back up the slope. Okay, now when it gets to the top, it's really interacting with that strong vorticity near the top of the ridge. And through the processes that I just described, the tilting and the stretching of the vorticity, you develop these counter-rotating pair of vortices, as I've shown in the cartoon there. Now, the interesting thing about those, and this is where the research we've done both in the lab with Domingos Villegas and his team and through numerical modelling, indicates that these two counter-rotating vortices can actually spread across the slope. Okay, so they're kind of doing their own things independent of the wind, but as a consequence of the wind interacting with the fire's plume. So it'll do this lateral spread, and you get the fire sort of propagating laterally across the slope, hence the term vorticity-driven lateral spread. And the other thing that goes along with it is because you've got this enhanced vorticity near the top of the slope and an enhanced intensity of the fire, you're generating a lot more embers, and those embers are being thrown up into the air. Sometimes they're getting caught up in the whirls and being thrown sideways, but eventually they're being picked up by the ambient flow over the top and deposited downwind. Okay, so what this actually means is when you have vorticity-driven lateral spread occurring, the main direction of spread isn't just with the ambient winds, it's going to be across, but at the same time as it's going across the wind, it's spotting downwind. So you almost have this two-dimensional growth of the fire. So what that means is you can get very large aerial growth happening and a fire escalating very quickly in terms of its pyroconvective output and so on. Okay. Again, sort of skipping over the details, but summarising the research that's been done around VLS. It's subject to a bunch of environmental thresholds. Okay, so 3 in particular. For VLS occurrence to happen, we need pretty strong winds, and as a rough guide, something above the order of 15 to 20 kilometres per hour. We need a lee-facing slope above about 20 degrees inclination, and we need the topographic aspect to line up with the winds in the right way, and roughly between 40 degrees either side of the wind direction. If your aspect satisfies that, then that's getting you into a very a situation which is very prone to VLS occurrence. Now, what these thresholds are about is really giving you the conditions you need for the winds to separate in the lee of the ridge and recurve back upon themselves, giving you that ambient horizontal vorticity, which the plume then interacts with. I guess another kind of threshold we could apply is one around fuel moisture content. And this really, I guess, is one moisture content, then, spotting's going to be a significant problem for you. All right, so let's go back to where we left it with our firefighters working on the flank of that slop over. But now, based on what we've just learned, you can see that they're on a pretty steep slope. It's above 20 degrees. The wind speed's certainly above 18 kilometers per hour. So again, satisfying that wind speed threshold, which was on the previous slide. The winds are lining up pretty well with that ridge line. And so the topographic aspect that the firefighters are working on satisfies the requirements in terms of the difference between the topographic aspect and the wind direction. And if you do a little bit of a rough calculation on the temperatures and humidities that were forecast, then you can be pretty sure that your fuel moisture contents are going to be pretty low. So putting all that together, this is really telling us that these guys, this crew there, are working on a patch of land which is prone to VLS occurrence. Okay, so once we sort of determine that they're in that sort of situation, we have another option, right? Instead of thinking about the fire spreading with the wind, we also now have to think about the fire sort of generating these vortices. And I should have mentioned, even though the cartoon says there's one vortex, these are really happening all over the place. And so there's the potential for the fire to spread almost perpendicular to the wind and directly over where the firefighters were working. Okay, so sort of two very different ways of thinking about the operational outcomes for such a situation. And so I guess two things or two different ways of looking at a situation that need to be taken into account when you're making operational decisions about how to respond crews and how to think about the way a fire is going to evolve and how you might manage it. So I said this was a hypothetical sort of scenario that I was doing, but I actually didn't really tell the truth there, because this is precisely the scenario that happened on the 5th of September 2020 near Bozeman in Montana at the Bridger Foothills fire. The Bridger Foothills fire led to a shelter deployment. Thankfully, there were no fatalities. They all got out with slight injuries, but survived. And you can sort of see there on the left a photo of the fire as it was escalating, and a reconstruction of the fire perimeter. I've put in the rough location of the hand line that the crews were working on, and you can also see where they were when they decided to deploy their shelters. But you can sort of see from there, the fire from where it was didn't really travel very far downwind. The majority of the spread is sort of across to the north and then further up the valley with some spots forming towards the east. Recently, there was a really fortunate capture of a fire on some cameras that are set up in California, part of the HP-REN project. HP-REN is the High Performance Wireless something network. But yeah, there's the website there. You can go and check it out. They have cameras set up permanently. And we just let this run through a couple of times. You can sort of see the fire entering that lee-facing slope and sort of churning across the top of the ridge and sending spot fires down ahead of it as it goes, showing you that sort of two-dimensional spread and a nice little fire eruption there at the end as well. I'll let it go one more time. It's pretty spectacular. All right, so I guess what I've tried to convey here, I didn't put any maths in as much as I sort of feel obliged to as a mathematical scientist, but I think it's important just to be able to, as Mel said, try and pitch these ideas to an audience in a way that's going to be useful for them when they're on a fire ground or thinking about how to manage the fire. Note that I didn't really mention any Australian context in this, because this is a universal phenomenon, a universal problem we have to face. There's another picture there of a vorticity-driven lateral spread event in British Columbia in Canada. So even though a lot of the research was initially done in Australia, it's become part of a more global research effort and addressing a global fire problem. So hopefully that was of some use to everybody. Thank you.
I can certainly say that Jason's work is of great use to us, and particularly that work he's talking about there, was a feature of our bushfire inquiry from 2019, and we're looking at how we can implement that, not just in an operation sense, but also in our planning sense. How can we treat these areas of the landscape to try and mitigate the effects of some of these extreme fire behaviour? So, perfect example of research into operations. Look, it looks like we are tracking behind time, but I will tell you that the next presentation is definitely worth staying for. So if you can't stay for the whole time, definitely come back and watch it online. I've just been sort of looking at some of the questions, and I think Simon's going to do a really excellent job of bringing this all together. So I have to be biased. I work for Simon. So Simon's actually been a really long term volunteer with the organisation. So since '94, which was one of our really big significant fire seasons. He's worked in this space for many decades, and he's even completed his PhD on bushfire patchiness. He's sort of led the fire behaviour capability within New South Wales, but has heavily influenced that nationally. While he's been with the RFS for a long time, he's also had a couple of stints away where he worked for the Bureau of Meteorology, setting up their national capability, and also with our national body AFAC. So at the moment, he's got a really large team, which includes predictive services, risk planning, my team, AFDRS, and a couple of others. He'll sort of present some of the work, which I think will bring this all together nicely. So over to you, Simon.
Thanks, Mel. I'll jump straight into the presentation, and great to join you all, and g'day from whatever time zone you're joining us from. I do actually, I've been having a look at the chat, and definite shout out to those Mexicans at 2 o'clock in the morning, I think it is. If you're still hanging in there, you're legends. Great work. So really, we've had a couple of presentations looking at the science from Mika and also from Jason, and then also John's shown us some developments we've had with implementing that into the Australian fire danger rating systems. And I'll sort of have a look now at how we operationalise a lot of this science. And I think from a perspective, what does it mean for the decision makers, and how we use this and keep it, like making sure we keep up to date with the new information that's available, what that means for the safety of our firefighters and also the community experiencing these fires, and but how do we actually practically implement these as well? And so I'll look at some of the systems that are available, but probably before I jump into that, it's been good actually having a reflection of some of the work by Jason and Mika, and some of those, it's going to take us a lot further down the track until we build systems, and particularly the work that Jason's done with VLS and how we map them and use them. But we do work very closely with these researchers, and particularly that they will be involved with us during major operations. And during the 2019-20 fires, I was on the phone quite a bit to Jason, seeking advice as far as fire junction zones, and when we have big fires that we're going to potentially join together. Mika is actually shoulder to shoulder with us as a researcher. She was also in there working with us operationally. And I think that's so critical, having the researchers involved with us operationally, and they understand the pain that we have in this space. And it's something we're going to need more and more. And particularly the challenge this group has of looking at extreme fire behaviour. As Mel mentioned, we're at the front line of climate change, and we're seeing these implications more and more. And as the vorticity-driven lateral spread Jason is talking about, Mika's done some work on nocturnal events and dry slots, and how we're seeing fires running hard overnight, like we're seeing during the day, and also pyroconvective fires, and particularly almost the exponential increase in the number of these fires we're experiencing. And what does that mean for the sorts of implications where we've got to make decisions about warning communities, but also decisions about pulling firefighting capability off the fire ground because of the safety of firefighters? And they're hard decisions. And particularly with the uncertainty of the science, where do we err on safety and avoid the cry wolf scenario, but also where do we just make sure that we need to make sure we keep our people safe as well? And so there's a real end to a lot of this science as far as how we implement it. So what I'm going to just go through is a couple of the examples of how we're employing this operationally. And in the first case, we've had a history of modelling and using it going back to the 1968 with the MacArthur model, and particularly in early 2000 we had the development of the Phoenix Fire Spread Simulation Model, which was a computer modelling system. New science came along, worked with the CSIRO, and particularly making sure we had better fire behaviour models in the forested area. And then we had the development of the Spark system and now AFDRS. So there's been this constant path of evolving and developing science into our operational systems. And there's been a few questions in the chat, and I'll try and answer some of them as we go, but particularly looking at these fire spread models. And there's been work done in 2016 with the Ember Transport. There's CSIRO models and rules of thumb we've been applying. With time, I won't go into, but Mika's already covered using access fire and also the improvements to the Vesta model. And so a lot of what we're looking at here is we have a platform now, which is the Spark system, which is a fire spread model that's scalable and tailorable. And I think one of the things that's really good is it's configurable with a whole lot of customizable templates that we can use to produce a simulation model. And it's dependent on a whole lot of those input layers, and I'll talk a little bit more about that later, and how we define fuel and how we put disruption layers in, looking at fuel moisture models, a whole lot of integration that we need to put into those systems. And for example, as Mika said, with the Ember Transport model, we have we've done a lot of work into how we translate that science into something that's practical. And for example, we were using the straight empirical spread models that Jason Sharple spoke about, and we have their limitations. Generally, they serve us well, but sometimes we get surprised by these situations. But then particularly not understanding how these embers are being transported properly. And in our first attempts at putting these into the simulation models, it failed catastrophically. And we went from a model that was often under forecasting to something that was massively over forecasting. It wasn't understanding the disruptions well. It was actually burning fires from New South Wales across to New Zealand, which is across quite a large expanse of ocean. And so the model just, it was a lot of work that had to go into the operational people as to how do we make the implementation of this science meaningful. And we've actually been able to achieve that, and we're really looking forward to using some of those, that system now operationally this fire season. The other part is also we're getting these models and having them so that they help us with decision support. And so using producing a user interface that is meaningful, and also interpretable by our operational people. And in some cases, there's good technology now. We can play animations, we can drape over 3D layers, we can show the influence of different fuel types. We can also start putting in and integrating a whole lot of different sort of suppression options that we can start looking, as well as different fuel management strategies we've had in the landscape. So we're actually finding this extremely useful as an operational implementation of this tool now. Still a lot of work to be done, but we're getting a lot more competent at using this system now. And John spoke about the AFDRS, and I think from an operational perspective, it's one of the key things is this has been a massive shift for us as a sector in how we use and understand fire behaviour. And we had a very limited system before that only looked at 2 fuel types. We've now got 8 different fuel types and a whole lot of different fire behaviour models. But from a fire agency's perspective, it's really easy to understand 2 simple models that had 1 line of formula each model. Now we've got 8 different models. Some of them are pages of formula. And so how do we actually, how do our people intuitively understand what these models are going to be doing? So there's increased accuracy. There's a whole lot of benefits that come with it, but there is also increased complexity. And so how do we balance that best with the implementation of the system? I think also one of the things we've done with our new fire danger rating system, because it's based around a fire behaviour metric, a rate of spread or flame height, so that we'll use our metric for each of the fire behaviour, and that's calibrated to be consistent across all the vegetation types. It's also now open to continuous improvement. So work that Mika and Jason do, and a whole lot of the other fire behaviour scientists, we can actually test that, and if they think there's a better model, we can implement it into the system. So that's a major change that we've got in our approach now that we have. So one of the other challenges we have is how do we make the underlying data work, and particularly it needs good fuel data and fuel understanding. And so we've got state vegetation mapping. In some cases, we're using the most accurate vegetation mapping that's available for a particular area. In other cases, we need to use satellite imagery. That's field validated and tested, and we patch together a mosaic of the best available vegetation data. But we still update that twice yearly. And in some cases, in most cases, we rely also on fuel models and fuel accumulation curves, which is an imperfect science, but it's better than nothing, I suppose. And so it's the best estimate we have, and we're looking forward to future improvements. And one of the things we found with the enormous fires of 2019-20, where nearly a third of the forested area of New South Wales was burned, with 26 million hectares. So we're talking huge amount of landscape of vegetation. Because so much canopy was removed, it wasn't actually following the fire behaviour models. And what we were finding, without that canopy leaf litter, we weren't getting as much leaf litter accumulating on the surface. But also without the canopy, we were getting a huge flush of shrub layer. And so visually and structurally, there seemed to be a lot of fuel. But where that fuel was arranged in the landscape was quite different to the models. And so we had to adapt. While there were models, we actually had to recalibrate and adapt the models in that case. The other thing, particularly for grass models, you can see there's we're resolving using remote sensing and reporting from landholders a much better resolution of understanding the mosaic of fuels in grasses. And we're using this remote sensing, and particularly looking at in our grassland areas, you've got natural ungrazed areas, and that occurs in some of our national parks and other areas, but a lot of it comes under land use, and so it's either cropped or grazed areas, and they'll have very different fuel loads. And cropped will have an increase to a peak and then almost disappear, whereas grazed will gradually decrease over time. And so how we map that mosaic within the landscape to most accurately have those inputs that we put into our fire danger rating system, but also we use for our fire spread predictions. The other thing we've been using recently is fire extent and severity mapping. So fires are heterogeneous in the amount of vegetation they consume, and so we're using satellite-derived imagery to come up with estimates of the severity of fire within the landscape, and that modifies our inputs that we put into our fuel dynamic models for our systems we use. We've built a system called Athena, and that's a platform within which we can hold a lot of these information and predictions, and helps us gain intelligence on the system. And it's an interactive and dynamic system. So if as soon as a fire or incident is reported, it goes into Athena, it will generate a point prediction. And then that fades into a whole series of other areas of examination. So particularly for aviation, there's a risk assessment done with potential issues with aircraft, looking at potential impacts and areas that could be threatened by this fire, and also looking at resourcing and resource capability. We've started to dabble and have a look at ways that we might use artificial intelligence to come up with optimum resourcing for these sort of fires, and what could our first attack success be with the resources that are available, and what could apply. But we've got a long way to go down that path. But it's an interesting toe in the water with using AI to help us with some of the decision-making processes. And so we come up with these fire modelling predictions, and we also, currently we're only ensembling based on uncertainty, based on the location of the fire and the time of the fire. In the future, we're hoping to come up with more accurate ensembles using the variability of weather and fuel inputs. And then that'll give us a map of the burn probability in the landscape, what sort of fire behaviour with flame height you could see, and also where's the ember impact areas. These then go into risk visualisation tools, and so looking at maps of the landscape as far as a probabilistic understanding of where the impacts could be and what sits under those impact areas. And then all of this feeds into a common operating picture where we've got map layers that show our decision makers the tools that are available for them. Another tool we're using at the moment is smoke dispersion modelling, and I was 46, remind me, Mel, the number of fatalities we had from the 2019 fires, but actually the number was closer to 400 if you look at the people that that were affected by air quality. And one of the things we're working on quite a lot more is how do we understand where those high air quality impact areas are, and how do we warn and prepare people to try and reduce the harm as far as impacts from smoke. So there are a lot of the operational tools we're using, and the other thing we're also looking at is how we use science best to prepare and plan and manage the potential risk of fires. And we have a process in New South Wales, in Australia, with our bushfire risk management planning. And so each of the local government areas, so we're divided into 52 sub-areas within the state, and they do a risk plan to try and understand the potential, the threats from bushfire, but also understanding what our assets could be at risk, and what is the relative ranking of that risk. And we had a system in the past that was largely based on matrices and estimates and value judgments. We've invested quite significantly in research to come up with a process within which we can quantify risk. And this is using fire spread modelling, so things like Spark, and then we will run thousands of simulations within a landscape where we put a grid based on where is the potential of ignitions in the landscape, and then we'll run it through dozens of weather scenarios to come up with an understanding of fire impact and fire load. We then intersect that hazard onto assets data with a Bayesian model, and that's a probabilistic tree within which we look at what is the vulnerability of these assets and coming up with a potential probability of loss of those different assets. And so we'll do that for life and structures, environmental impacts, economic, etc. And so there's quite a lot of work that's gone into developing that risk management planning tool. And we've actually, as well as those 52 bushfire management committees, we have statewide products and also a whole lot of local tools that we've got available. So here's an example of the risk modelling platform. In this case, it's looking at roads as an asset and linear features. We can look at power lines, water features, a whole lot of other different features that we'll run through that, and it will show us our lowest to highest risk in the landscape. And that helps prioritise the treatments that we'd be applying. And so one of the things this model also gives us is an opportunity to gain future fires before they occur. And so based on that probability tree, we can now put prescribed burning into the landscape. So we can put strategic mechanical works and actually see where is the best place in the landscape that we can have as far as getting that risk reduction. And I mean, that's also another thing that we have in sometimes we may be limited to how much burning, for example, we can do. And so which are the ones that we should prioritize in those times. We can then look at all of these different treatments and come up with an idea as far as how much that reduces risk and also what's the economic value of it. So really producing a holistic business model for understanding where do we get our best bang for our buck in trying to reduce the harm of fires before they occur. And finally, to wrap it up, there's a whole lot of research we're doing in that risk modelling space as far we can improve that Bayesian model, that feeding in improving our fire spread models and also understanding the forecast. And particularly at the moment, we're modelling based on historical weather. One of the things we're going to need to start doing is looking at with climate change future weather and how do we apply that into our modelling, and particularly if you look at strategies we've put in place for structures, buildings that are going to be there for decades or more, what sort of risk are those structures going to be facing into the future? And I think that'll do me for this afternoon, evening for us. Thanks. And I'll hand back to you, Mel.
Thanks, Simon. I think that it's probably answered quite a few of the questions in the chat, but happy to take any others. In fact, and maybe this is still part of a question to you, Simon, and then also Tamika was one of the original ones about validating models. And so how to, particularly with our, as we're coming into implementing Spark, what are some of the challenges, I guess? You alluded to a couple, but have you got any more details there?
Yeah, thanks, Mel. I think from an aspect of validating models, what is the fire actually doing? And we've seen some images of using the multispectral scanner or the line scanner. And so that's one of our truths is, did the fire actually do what the model was saying it was going to do? And that's how we build confidence in the application of use of this. It's testing against historical fires, but I think the thing is that we need to be careful the data set within which the models are built on, and if we're testing it on historical fires, we need to test it against fires that weren't part of the model data set. We need to have almost a test data set of historical fires. And so there's lots of opportunities for us to evaluate the models.
Thanks. Mika, did you want to add anything to that response?
Yeah, sure. I mean, I guess there's always been the perspective from the Met community that a lot of where meteorological modelling has advanced over, 80 odd years is because of verification, and because that verification has been a really robust part of the development of the models. I think in fire it becomes really difficult because if you're going to verify a model, whether it's a fire spread model or an ember transport model, a lot of the models implicitly have the assumption that no suppression was done. So you're almost restricted in the subset of cases that you can use to one where nobody tried to put the fire out, because then you ended up with a different outcome. And we know, I mean, in Australia it's difficult to actually look historically at a set of fires where we've got really detailed information. And as I said, with the meteorology component, we actually don't have that many observations because it's really difficult to take observations in a fire environment. So we've got a limited amount of information that we can use. People are probably aware, in America, they've got the big, assuming Trump lets it go ahead, they've got the big project plan to go out and take a whole heap of instrument measurements inside fire plumes and in large pyros CBs, because that kind of data becomes really important. So yes, we're trying to verify. Yes, we have a limited number of cases which have got the right data. But I think as we evolve and as we move forwards, as we want to verify the models, we're actually going to get a lot more decisive and a lot more deliberate about the kind of data that we're taking and measuring so that we can verify more systematically.
I might just add a bit to that. Thanks, Mika. That it's a really good point, the effect of suppression. And I think it's one of the challenges we have with the models we build is that there's a sweet spot in the prescribed burning space where we're happy to let fires run and do the things they can do. There's a spot when we're not happy and we're going to be actively suppressing and sometimes buggering our predictions because they're putting fires out. But then there's a spot beyond that where suppression actually doesn't have much of an effect. And fires are largely running without that, and which is in that more extreme end. And I think there's a lot of opportunity. And from an empirical sense, probably the tragedy we've had in the past is that a lot of our science has been based around those really low end, and then we've extrapolated up to buggery. And which way does the curve go? I don't know. And we're just drawing straight lines or curved lines where there's no data points. I think now, particularly with improved remote sensing, we've got a better observational capability to start building these empirical extreme spread models, and there is going to be a window where the suppression is just not being effective. So I think there's a lot of opportunity for us in the future in this space.
I think this probably leads quite nicely into the question that Fabio asked of John, but just before I check to see if they want to add some more to this, there is also this challenge, I guess, with the verification of models as we start moving them into our day-to-day business decision making. And when we're dealing with Treasury or government, and we make changes, and those changes we all see as improvements to the model, but are really hard to justify why the answers are different. So in an operational sense, we kind of get a reset every time we get to a new fire. But when we're using this as part of our business model to justify our expenditure and mitigation and all of those things, it becomes even harder to, and more important to validate these models and to be able to know the differences between what are the changes we're making when we update and improve our models. I might just ask, so Fabio asked John about the suppression indice. Do you want to, because I think that's probably quite topical to what Simon and Mika were just talking about.
Yeah, the suppression index. It's so what it does is it measures, well, it gives you a forecast for the likelihood of suppression success at initial attack. And so we're using empirical models where initial attack success is defined as either an area, so the fire's been put out before it's got any bigger than 5 hectares, for example, or the fire's been put out before it's spread for longer than 2 hours or 4 hours. So these empirical models generated by Matt Plakinski at CSIRO are the ones we've used. And we're constrained quite a bit, actually. Since we've got a national program, we need to have input data to produce a forecast that's available around the whole country. And so there's a bunch of suppression models that are out there which are quite good, but we can't necessarily use those models because we don't have the data available. So we're constrained to only use models which have data that we can actually use. We can actually get our hands on and actually use to produce a forecast. And so the downside of that is that the models are quite crude, and we don't use information such as knowing what suppression resources are likely to be put onto that fire. So our models use response time, so how long it actually takes to get to the fire, and we use that to determine how big the fire is going to be at initial attack. Yeah, so the models we're using are empirical models. They're not deterministic models. And so they do work, but it's not great. But we use what we can. Yeah.
Okay, thanks for that. There's another question there for Jason, which sort of triggers about 2 projects he's working on. Did you want to provide a bit more information about the implications of VLS for the field break planning?
Yeah, sure. So I sort of chatting in the chat there, but we're currently working on 2 projects in collaboration with New South Wales RFS and other partners, and so it's really trying to get a better understanding of how we can mitigate the effects of VLS, and in particular, sort of understanding VLS as a key factor in escalating fires, and so. By understanding where VLS is likely to occur, then there's potential for, I guess, prioritising fuel treatments and those sorts of activities around those areas. We don't know if reducing fuel load will actually stop VLS happening. My guess is that it will. But yeah, that's where the research and the science comes in, to really trying to answer those questions. And then there's the other sort of economic and to sort of throw at doing those sorts of situations as well comes into it as well. But and it's, for all the work we've done on VLS, we've never really taken a close look at the role of fuel load. So that's one of the projects, just to get a better look at that. And the other one we're working on, I guess, is how VLS can ruin your day. Put it that way. You can, have every good intention of putting in a backburn to try and to stop a fire. Often when there's no other options available to you. But if you do that in the wrong place, in a place which is prone to these sorts of things happening, and you don't necessarily understand that well, then you can actually, instead of having the desired effect of suppressing the fire, you can end up with a lot more fire in the landscape that you didn't want very quickly. So it's really trying, I guess, to understand, looking at historical instances of where backburns have escaped, and trying to understand how often VLS played a role in that. And the other angle on that is, if you're trying to do a hazard reduction burn, strategic burning to try and reduce fuel loads, again, if you try and do that in a place which is prone to processes that you don't necessarily have a good understanding of, then instead of mitigating the fire the season ahead by reducing fuel loads, you end up actually creating an active fire. So your hazard reduction burn becomes a wildfire incident.
Yeah, and look, and sorry, Jason, that really was just a shameless plug for get you to talk a bit more about the research that we're doing. And in terms, I guess, of where we pick in the landscape, probably a lot of it has been ridgetops, but we probably, and from a local perspective with local people planning, they're probably accounting for the fire behaviour that they've seen, but we're really, trying to look at a more strategic level about how can we ensure that those burns that are taking place in the landscape, because we have switched to a lot of our burning to be closer to the things we're trying to protect, but those ones that we put in the landscape, how can we align them to these areas as well, so that not only are they stopping particular, that there's a whole range of extreme fire behaviour, like ember spotting across ridges, but also some of these other sort of factors. So if we can line the same areas, hopefully we're stopping a whole range of fire behaviour. So that's the work so we've actually changed our policy to include a zoning system, and we've got people applying these, and we're going to give all of these examples to Jason, and hopefully he's going to tell us that all the local knowledge has come up with some really good solutions. Yeah, work in progress.
Yeah, and I guess the other thing to emphasise too, even though I sort of highlighted BLS today, there are several known modes of dynamic fire propagation. Fire merging, fire coalescence, spot fire coalescence, fire eruption. So yeah, and a lot of these things sort of tend to be more likely to happen in similar landscapes. So it becomes a problem of sort of, do you address each one in isolation and hopefully they all line up somehow, or do you really need to go out and address each one individually? So yeah, it's a tricky problem.
Thanks, Jason. I can see that we've got one more question online, but I can also see that Marco is sitting there with his camera on. So would you like to ask the question you've got about Athena, or is there something specific you'd like to ask from Simon?
Hello, everyone. I missed the slide because it passed too fast, and I would like to understand all the steps, if it's possible to return that. Thank you.
Yeah, thanks, Marco. I did skip through very quickly. That's probably a presentation in itself, talking about what we're doing with Athena. It's a platform we started on after the 2019-20 fires, particularly looking at how do we start to set ourselves up using the systems to build an intelligence capability. And so it's using the fire spread modelling as the basis so once we've got a known ignition, looking at what is the footprint of potential impact of that fire, and then it interrogates a whole lot of data sets, looking at what are the assets that could be impacted underneath that. But then that also integrates with our common operating picture. And so we have our vehicle location system, so you can see where are all the fire trucks, where are the aircraft, so where are the suppression resources within the landscape. What we're looking at in the future is how can we use this leveraging off some AI capabilities to come up with estimates of what sort of resourcing might we need from an ignition, or to sustain a campaign with those sort of fires. But there's still a long way to go with that. And I think one of the challenges with AI is it needs big data to make sense. And we don't have enough fires and data that, in some cases, and, it's still a whole area we need to explore. But at least at the moment, we've got a system we're using operationally that gives a subset, but we have a vision in the future as the sort of things we'd like to use it for.
I think that's all the questions that were in the chat. Is there any other questions that people would, and I'm not sure whether I can see whether people are asking questions. So if you've got anything, just speak up and hopefully we can work it out. Look, I think that these sort of presentations show a lot of, I take for granted, I think, a lot of the time that I have the opportunity to work so closely with our sort of research community, and it's a cross between, straight academic and then our sort of more operational sort of research organisations. And, we do have quite a number of sort of ongoing research programs, although I guess the more that we do, the more questions we ask. And it's been really fantastic for me to have this sort of overview and look at some of the things that 5, 10, 15 years ago didn't exist. So in the Australian context, because we do like to think that Australia is quite different, vegetation types and those sort of things, and a lot of our sort of modes of operating. But as Jason's shown, there's a lot of things that are applicable elsewhere.
So Mel,
So I have,
just on that,
yep.
just to follow on for that, I think it's important for us as researchers to acknowledge the input from fire practitioners as well. I mean, it's really important that the research we do is heading in a direction that is actually going to be useful. I tell everyone in the team, if what we do doesn't end up in the hands of people who are going to benefit from it, then what the hell are we doing? So yeah, it's really good to have that sort of operational and practical perspective to sort of guide our research, and throw that out to everybody in the sort of international practitioners as well. If you've got things you want to talk to us about, then don't be shy.
I might add as well, Jason, one of our themes we've got, like we engage quite heavily with national research institutes as well as our state ones, but it's useful, it's usable, and it's used. And so that's a really important part of the research design and development. How can it be used and put into the end? And from us, from an operational perspective, I mean, Mel's been involved in that risk planning project. While we've spent decades in developing the concept and research and theory behind it, it's probably been an over $10 million project over the last 2 to 3 years in making that research concept into an operational model that we can actually deploy. So it's a huge investment with some of these things we need. And I mean, the research that John was talking about with AFDRS, really the seed of that was back after the Black Saturday fires, and it's nearly 2 decades of work that we've put into getting that implemented. And so it needs a huge commitment from the research institute, but also the agencies and that strong partnership to be able to implement these things.
We've found in those workshops, just the interaction with people, the continued interaction has improved the AFDRS a lot. So it's been really valuable to have that continued interaction.
Oh, well, any last call for comments there? Otherwise, Fabio, did you want to wrap it up?
No, maybe I only have the last Simon speak understandable. I think it's important that we as a practitioner can see in the fire science. So it's very important. So this is the main concerns that we have is we are seeing a lot of the developments when we talk about fire science, and in the last few years we had a lot of developments, but it's very important that in this case, if we want to apply this kind of the developments, it's crucial that or could be understandable to the practitioners. So we need to find a way to communicate with these two different worlds. We have a gap between the researcher and the practitioner when we try to apply all this development. So I'm so glad for this webinar. You know that for me that I wanted to see. In my opinion, again, I think Australia today represent one of the best example when we talk about all this kind of the developments. So we have lucky because we will have all this video available in few days with the YouTube channel of the project. Thank you again for your participation, for everyone in this case, but mainly to our speakers. So I know it's late in Australia, 8, 9 p.m. maybe, I don't know. But yeah, it's late, and thank you very much for your efforts and or your collaboration. I think all these speakers, you have a lot of contents in the and publications available. So I think it's easy. We see all this work and keep in touch because we will need your developments. I don't know. I don't have nothing to add. I don't know if you want to say something, but from my side, and in this case, behalf of the NERO project, I want to thank you again, and again, I'm very glad for this webinar. Thank you very much for all these presentations and the participations for everyone. Thank you very much.
Thank you.
Happy
Thank you,
Portugal
Fabio.
Day.
Thanks, Fabio.
Thank you. Bye bye.
Thank you.
Bye bye.